So, dear colleagues, I would like to introduce our next speaker. It will be Brent Brout. He will offer us a presentation about completion technologies like a tool for energy transition, case and studies. Brent, take your right to offer your presentation. Welcome.
Excellent. Thanks, Lilia. And thanks for the entire SBE committee in Russia Caspian for giving us this opportunity to present. I'm just going to attempt to go in speaker mode here. Bear with me, everyone.
Yeah, we hear you.
There we go. Can you hear okay?
Yes, hear and see.
Perfect. Can you see my screen, full screen now?
Yep.
Perfect. So if there's any questions, please just, you can stop me as I'm going through, or perhaps just take notes for the end. I should go through about 22 minutes. The purpose of the call, or the topic, pardon me, is going to be about the energy transition that everyone's been talking about so long. Is really a broad topic, and sometimes it's full of good science, and sometimes it's pretty fluffy in terms of the greenwashing aspect. So what I'm going to try and dial into is discussing the completion technology. And when I talk about completion, it's well completion for the upstream sector of the oil and gas industry, because we're trying to actually have this transition into a greener, lower emission energy economy, but we still have to actually produce the oil and gas for meaningful aspect. So I work for a company called InflouControl. It's a Norwegian company. I'm based in Abu Dhabi myself, and I'm the CCO for the company. So I think to start off, I'm going to start in a broad sense, and to talk about a transition, it needs to be exactly that. We've got 7.7+ billion people in the world. And when we're looking at the aspect of the world, depending where you are and the luck of the draw and where you're born, you have a real different view of the world. And when everyone's talking about energy, it means many different things to many different people from many different countries. So if we're looking at almost 700 million people in poverty, there's a massive amount of perspective that needs to be taken on this. You look at the energy that's required for heating, the energy that's required for keeping people safe, allowing lights to be held for electricity. Most people around the world that are not in the luxury side of the world, they want to be able to just keep their families safe, to provide an ability to send their kids to school where there's lights, the ability to have a warm home, and heat and energy to actually be able to cook in a safe environment for their family. So when we're looking at this paramount transition shift that the world's talking about, we need to actually understand that the majority of the world has a very different perspective on this lens. So when we're looking at this energy mix, I chose an older slide from the IEA. The data's changed slightly, but not on the macro level. What you look at on the top side from the IEA here on this graph, you're seeing that the oil sector is still a massive portion of this mix. And as you move from left to right on the axis, you can see the natural gas impact. We need to have a transition on the oil and gas impact on the emissions, but the world still needs the oil and gas products for a variety of aspects, not just on transportation needs. So all of this energy transition in the mix really needs to have an ability to make an impact on reducing the emissions now, and not wait until 2050. So one question we're going to talk about on this discussion is, how do we escalate in a very economical fashion lower carbon oil now, not waiting until next year, not waiting until 2030, not waiting until 2050. We really need to apply the technology to aid in this transition. And when I'm talking about the transition, we're talking about this transition of lowering the carbon impact for oil production. So one key aspect that you can dramatically lower the emissions is reduce the gas flaring. Why are we actually producing the carbon out of the earth to then burn it and then try to figure out a technology that actually needs to capture it? It's almost insane when you think about it. You're bringing excess gas to surface, and then you're burning it because you have no way to capture it or hold it or transport it. And then that equals emissions. So if you can stop the gas from coming to surface, leave it in the ground, you have less emissions to actually tackle topside, less CO2 associated from that. And then you don't have to actually start to try to capture the unassociated, unwanted CO2 from flaring. Reduce the excess water production from our oil reservoirs. The more water we produce, it A, is not economical, you're not selling it. B, you have to use electricity to get that water to surface. You have to then transport that water on pipelines or trucks to a treatment facility. You have to treat the water and then also dispose of it into reinjection wells. So it's a bit backwards to look at why we're actually trying to produce all of this gas and water to surface. And then we need to actually improve the oil recovery with less wells, because all of this, when we have too many wells involved, you are then going to have more associated CO2 for each well to get that associated barrel of oil. And then if you actually can get away without having to do as many well interventions into the lower completion to actually do changes, that is associated CO2 with the trucks, the personnel, the time and the energy required. So transition requires change. And I'm going to show this here. You see 10 bottles. I chose Perrier. It was just a nice, pretty picture. But you have to think, is the oil company in competition with the water industry? Because on average, it's 10 times more water than each associated oil produced. Now just pause and think about that. 10 times more water per each oil barrel produced. This is a really, really poor energy exchange to try and get the water and oil to surface when you don't have to, because it requires so much energy, and that energy has associated emissions. So if I take a step back and I'm going to talk about how we are applying technology to help and support this energy transition, we're looking at existing oil reservoirs around the world where they have already had a significant investment into these oil reservoirs. But how can we impact beneficially by reducing the environmental associated emissions? So the technology that we're using, and I'll talk about here in the energy transition from a completion aspect, is the AICV technology, or autonomous inflow control valve, which automatically chokes the high water zones and allows the oil saturated zones of the well to be produced. So one example here you'll see on the left is in 2020 alone, the documented measured results was over 2 billion liters of water saved. So it could be much bigger than that around the world as technologies are adopted. But just in 2020 alone, from our company, we were able to actually save 2 billion liters of water. So in perspective, that's 800 Olympic swimming pools. Now, if you average an 800-meter deep vertical well and you're producing that to surface, that's 8.3 million kilograms of associated CO2 emissions just from the energy of the pumps to produce it. Just from the pumps. That's not treating the water, that's not sending it to the treatment plants, that's not the energy required to re-inject it. That's just the lifting costs. 8.3 million kgs of CO2 emissions. Now, if we look at gas, in the last 4 to 5 years, we can document, which is a bigger number than this, but this is what we documented. By applying the technology, we were able to capture over 35 billion barbecue gas tank equivalents. And we use barbecue gas tank equivalents because most people around the world have a barbecue and you have a gas tank beside it. To visualize how many volumetric versions of this gas tank would be saved. That's 1.1 billion kilograms of CO2 emissions saved from not having to be flared. These are crazy numbers when you look at it. So I'm going to show you a video, so please let me know if it comes through, on how the technology is deployed. When we assess the reservoirs and look at, can we apply a technology to help reduce the water and the gas from being produced, it's a long engineering approach that we look at. First of all, is there enough economical oil saturation remaining in the reservoir? That's the first important part, because we haven't unfortunately found a way to make oil into water yet. If you have a solution, please let us know. When you look at this animation here, open hole wells without a completion, they don't have control on the unwanted phases of the fluid. And you can see here it's showing bottom water coming into the reservoir and into the wellbore, pardon me. And then as that water ingress comes in, you start producing a lot of water. And as you pull harder on the well, you'll produce more of the bottom water. And the easy way to resolve that is choke it at surface. But when you choke at surface, you do not access the oil saturated in the reservoir section. So by applying the autonomous inflow control valve, the valve manages the uncertainty in the reservoir. So when you get water in a section of the well, the valve will become more restrictive. And where there's oil in the section of the well, the valve will become relaxed and stay open. So as you can see in here, the main flow of the reservoir fluids, if it's oil, water, gas, or a multi-phase composition, will flow through the valve, roughly 97%. And then a small amount goes through the side outlet, the LFE, or the laminar flow element, as you can see on the right-hand side of the screen. Now, the fluid properties of this multi-phase flow that goes through the valve will then have a certain pressure drop through the laminar flow element. And that will create a pressure or force pushing upward on the piston. Now, as you have the oil moves through based on its viscosity and density and creates a certain pressure drop through the laminar flow element. Now, in this cartoon, you're going to see here the water is showing a rapid ingress. Now, as the water has a lower viscosity, you can see it's going to create a higher force on P2 and become more restrictive and i.e. choke off the valve. So what that means is that when you have the valves in between completion packers, mechanical or swellable, they will then isolate those sections of the well that might have unwanted phases such as water or gas or both. And then the valve will start to become more restrictive. So you don't have to choke your well at the wellhead. The choking occurs along the completion section so that you can actually remove or reduce the amount of unwanted water and gas, but the oil saturated sections of the well will be allowed to produce. As you see in the cartoon on the far right, it's showing a gas coning breakthrough at the heel. You can see in the middle, you're seeing water breakthrough at the center. Now you can see that's isolated with these swell packers in the animation. When you have the oil there, it needs to have the ability to be produced. And the valves will allow that ability to be produced without producing the unwanted high water or gas sections. And if you have a very late life reservoir where you need to produce more of the water, we can make the valve more relaxed so you can produce a higher water cut, but you don't want to produce the 98, 99% water cuts in the zone. So the whole premise is enable the reservoirs that you have, the oil wells, to produce more net oil. You produce less of the unwanted phases, and then you don't have to pump the water to surface. You don't have to flare the gas. You actually allow the reservoir to be depleted in a more economic phase. So you can see here, I've just got a snapshot where you see isolated in between the sections. So you need zonal isolation to make sure that the water doesn't flow everywhere or the gas flows everywhere. And the valves remain open based on the fluid viscosity and density of the oil compared to the water and the gas. And the valves will be designed for the reservoir. So if you have a different reservoir, Sakhalin Island, or you have a different reservoir in the northern parts of Russia or in Turkmenistan or Azerbaijan, they all have different reservoir properties. We tailor the valves according to the reservoir. We design it on the reservoir depletion strategy and then apply it. Now, as you can see in this exaggerated cartoon, as long as the reservoir is isolated with good compartmentalization, packers matter, by the way. Bad packers will not allow this because the valves are very robust. But if you have the phases flowing from one section to another, the valves will close if they see water and gas or choke restrictively. But the great part is when you have good compartmentalization, the valves will allow you to produce much more economical wells with a great amount of reduction of emissions because you don't have to have the unwanted water or gas to surface. And it's very simple. So from a deployment perspective, it's low cost. The payback period is very fast. You don't have to have excessive people on the rig, and you run it in just like you're running in sand control. So you can see here, there's a sand control filter that filters out the reservoir section, goes through a small housing. It's about 18 inches long, and you isolate the reservoir compartments with the packers. The fluids flow through the reservoir, the screen filter, into the housing through the valve, and the valve behaves as it's designed, stays open for the oil, becomes more restrictive as the GVF or gas volume fraction increases or the water cut increases. Now, it's all about the economics. It's not about talking about what we're going to do in 2030, what we're going to do in 2050. We need to do this now. And there's so many wells shut in. There's tens of thousands of wells shut in around the world already. And we need to get the oil out in an economical and environmentally better fashion. So this example here is showing you how to unlock the economic decision-making process from existing assets. When I say existing assets, that's wells that are already drilled. They could be 5 years old, they could be 10 years old, they could be 15 years old. This is an example of 3 real wells. They vary from 8 to 12 years in age. This is at $70 oil. The extrapolation over the 3 years with discounted performance over each year, it's over 8 million just in increased oil production. 3 million at $1.50 per barrel water handling treatment costs, doesn't handle any lifting costs. And the power requirement that's not in this calculation is huge. The power to pump the surface, the power required to treat the water and then to re-inject it. This is just on 3 wells. The payback period on this retrofit application within these 3 wells is a couple months. This is where we should be focusing our efforts in the oil industry in terms of actually making measurable and meaningful transition benefits. So how do we do this? You can see in this slide, we're showing a lower permeability zone and a higher permeability zone. So when we look at it, we just have to do proper engineering. We have to understand, where is the fluid going to flow from in my reservoir? And then how do I manage to produce more of the oil for longer without having to intervene into the wells? So we know that there's going to be non-uniform production due to variabilities in the perm. So we have to understand, how can I handle this? Before you run sand control or screens to filter out the unwanted particles, but that does nothing to discriminate the phase, because you do not want to produce the water. And if you produce all of the water and start pulling harder on your well, you start to cone much quicker. So when you have these high perm zones, how do you actually stop them? Well, when you go in and you apply this technology, that will take care of the unwanted zones automatically. You segment the well depending on the length. You add the certain amount of valves depending on the flow rates. And then the differences between the perm becomes a non-issue, because the zones that have the unwanted phases, such as a water or gas breakthrough in the higher perm section of your reservoir, become managed in the well without any intervention by the autonomous inflow control valve. Then the sections, you might have a lot of stranded oil stuck in a lower perm section. They're going to now be enabled to be produced. It's as simple as that. There's no control lines to surface, so you don't have to change your wellhead, don't have to change your completion design, but you might have to change your pump, because when you stop producing so much water, you can actually downsize the pump required to get your reservoir fluids to surface, which is cheaper and less electricity to pump the surface fluids. Now, when we're looking at this from a global perspective, you have to look at the carbon intensity on the electricity. And this is just an example we use because we help our customers all over the world try to measure the impact of their CO2 emissions. So if you look at Ecuador versus Norway, well, Norway is blessed with Mother Nature that has a lot of hydro. So they get very low associated CO2 per kilowatt hour. But in Ecuador, you can see it's 10 times more than the Norwegian. So these are figures that you look at. Now, the whole question is, you're pumping all of these fluids to surface. And as I mentioned earlier, the oil industry is probably one of the largest water industries in the world. And then you have to pump it to surface, costs associated money, costs associated CO2 emissions, and then you have to have even more money and electricity to treat that water and then re-inject it. And then there's all the technologies talking about trying to capture the CO2 that you've just burned by just trying to pump the unwanted water. So when we look at this from a perspective, these are 2 examples of public case studies that we put together with our customers. The one on the left is from the Middle East, the other is from an operator in South America. You can see on the right-hand section of each of these case studies, it's about measurable results, because an oil company shouldn't be a water company. And we're in the oil industry to produce the oil at the lowest possible cost and the payback time as fast as possible, and recover as much oil as you can. But the economics matter. And we do not actually apply the projects if we can't help the oil companies make more money. So you can see in this case, every application we go to, we can document and quantify the application in terms of economics from the payback period, the oil increase recovery, and the results from reducing the water and gas and associated tonnage of CO2. And all of this is really critical for this energy transition, because if you look at what Equinor has come out with in the last few weeks, BP's CEO has come out with in the last few weeks at the conference that's going on in Houston right now, it's all about funding a transition. And most of the oil companies need to do something now, not in 5 years, 10 years, or 2050. So I'm going to talk about a case study. This is documented in the IPTC 20195, so it's public data. The challenge: this well's been around for 13 years. The well was shut in due to high GOR, gas oil ratio. It's in a carbonate reservoir and a very light oil, 0.45 to 0.65 centivoids. This is ultralight. It's encroaching on the gas phase. It's a 1,500-foot horizontal open hole. And the solution, after much review within the operator, was to do a retrofit. So the existing well is a barefoot completion. So when we look at this approach, the first question is, do you have oil left in your reservoir? This is an existing asset. So we look at the data, and the operator ran a log, an FSI, to understand the perm profile and the oil saturation. So you can see here the permeability log overlaid with the saturation. And then on the bottom was the design that we approached in terms of how to segment the reservoir by packers. And the packers we used was a mixture of mechanical open hole packers and long swellable bonded packers. So you can see we segmented the reservoir into 10 sections. We applied 22 dual AICV joints due to the flow rate requirements by the operator. And then we did an acid treatment prior to the AICV installation. And a key point here is the operator flowed the well back before running the retrofit completion to ensure that there was no redistribution of the gas and that oil actually encroached back. They turned the well on, tested it, and the gas was still there, over 10,000. Now what you're seeing here on this next slide is, this is the log data. The pre-retrofit of the autonomous inflow control valve into the existing 13-year-old wellbore. You can see that on the top, you can see there's very good oil saturation on the top log. On the bottom, you can see how the AICVs managed the big gas breakthrough and enabled the wells to then produce the lower section. So if you look on the graphs on the far right, you can see that upon the retrofit completion into the existing old well, the well that had stranded hydrocarbons at the toe section were enabled to produce 5 times more oil from the lower section of the well and reduce the gas roughly 90%. What that enabled then is the economic payback was in weeks. They paid the drilling, workover, rig, and completion costs in 3 weeks. The well is stable for over 4 years. The GOR was reduced by 90%, and they didn't have to drill a new well for this. The existing surface infrastructure was able to be used. Very low payback. So this is a great example of enabling technologies to help fund the transition in towards lower carbon oil. Here's case study 2. It's a different application. It's roughly 4 decades old brownfield carbonate oil field. The wells were shut in due to high GOR. It's a light oil, roughly 2 centivoids. The retrofit solution chosen by this operator in IPTC 21411, as you can research, was to utilize AICVs with combination of just swell packers. And the results from this application, as you can see, we anonymized the wells from A to G. The pre-retrofit application of the valves to manage the unwanted gas was shown on the second column from the left. And then you can see some of them did also have water challenges. So you can see on average, the gas production reduced by 83%. This is huge because you know the associated CO2 emissions from burning the unwanted phases. The water production was reduced by 83%, and the oil production was increased by 32%. So the achievements on the goals here, Did we reduce associated gas in the emissions? Yes. Did we reduce the water? Yes. Could we downsize the pump to use less electricity? Yes. Did we increase the oil? Yes. Did we improve the profitability? Yes. These are all key approaches. So the conclusion, in this energy transition, the oils required for the coming generations. I've got kids and they're all focused on renewable energies and whatnot, but I'm trying to be honest, the oils required for pharmaceuticals, it's required for transportation, it's required for building, all of the products we're talking about on our computers right now, the phones we use, there's oil in everything we use today. It's going to be required to have a transition. We need the lower carbon oil now, and we can do it. The technology's here. We don't need to go and reinvent anything. It's all about changing our mindset, taking some time to engineer the application, not waiting 20 years. We can do this now. The technology is available. We can lower the emissions in the CO2 within a week of applying the technology into the well. So we get pretty excited, as you can tell from my presentation. We're pretty excited as a company because we're in the oil industry and we're proud of this because it fuels the world. And we need to enable our customers to make the profit to then invest into the alternative energies. So that's all I have. Thank you very much.
Yes, thank you very much, Brent, for your presentation. Maybe it is not as easy and clear for a first introduction as previous topics, but it makes sense for sure. And can you please summarize briefly how this technology could provide us with energy transition, how it brings us to our target?
Yeah, so I think when we look at the energy transition, the energy transitions, if we're going to renewables, nuclear, solar, wind, it's all about sources. And I think before the transition occurs, we're going to have to look at how you fund the transition. And if I go back to one of the earlier slides, the requirements for actually going to alternative energies actually requires a huge capital spend if we're looking at private companies or we're looking at governments. So I'll go back to the beginning. If we take this slide, and there's a variety of slides from the IEA, we are not going to escape using hydrocarbons in our coming lifetime. But what we need to do is dramatically have this transition of lowering the emissions associated with it before we actually end up getting too far down the line where we continue to increase the emissions to the point where this 2 degrees Celsius is even worse than everyone is talking. You see the COP26, everyone was reviewing how they're going to make changes. The problem is no one has a replacement for this transition yet. And if we wanted to have a transition, I use the analogy, it's not like Harry Potter on 9 3/4 where you can magically walk through a wall and you're in Hogwarts. You actually, it takes a significant amount of money and a significant amount of engineering to actually achieve that. And if we look at the transition around the world, the electricity grids, for example, it's trillions of dollars that are needed to invest. So in this transition, what we need to achieve, and with my hand on my heart, is lower as much carbon as we can from oil and gas, utilize the profitability as fast as possible to the other technology from a research and development standpoint, and then actually be able to fund it without putting everyone into debt, raising too much taxes on everyone as individuals, because the combination of profit and the environment has to go hand in hand. But we need to think clearly about what can we do now. And I know I'm from Canada, and I look at all of the technology they're trying to apply for capturing the carbon. When you can look at, you can reduce the amount of carbon you're putting in the air. Stop, like it's back to the engineering philosophies on this transition. Go to the root of the cause. And if you have a lot of the carbon in the ground now, and you don't need to produce it, and you don't need to burn it, you don't need to treat it, why are you? And it's just an honest question. So transition in our view is also a mentality. because you have to transition your thoughts first.
Thank you so much, Brent. Especially I loved your comparison with water production. And there is a question from our colleagues from Igor Moskvin. He asked you, what is the price range for your technology installation?
That's a good question. Thanks for the question, Igor. It depends on how many valves on the well. So if the well is a very long well, we'll need to have more of them. If there's a well with high flow rates, it can vary quite a bit, 4 to 5 times difference in price. So on the case studies, case study 1 that I showed, the payback period on that well was 3 weeks, 3 to 4 weeks. And case study 2, the payback period was 3.5 months. Very different production rates on that. So yeah, it varies, it depends, yeah.
Thank you very much for your answer. And
Yeah, one additional question from Igor Moskvin too.
Yes, please. Yes. Can you install it in unconventional reservoir?
Yeah, so you could install the technology. The first approach we look at, as long as the unconventional reservoir is connected to hydrocarbons. When we look at unconventional reservoirs, they're that because it's not a standard sandstone or carbonate formation. So you do need to create some kind of perm pathway to actually have the hydrocarbons get out. So as long as you have connections, the installation is not a problem, vertical, deviated, or horizontal. It's more a matter of, as long as you think you have access to the reservoir, if you've already fracked the well or you need to frack it again. So we'd review that reservoir by reservoir, yeah. So there's not an issue with installing it. The question we would look at from a reservoir perspective, if there's access to the hydrocarbons.
Thank you again, Brent. And